All right, it's time. Welcome, everybody. You have found your way into the February edition of the University of Lowbrow Astronomers. I'm Charlie Gilman, the club president. Seems like it's been forever. Someday I'll get myself out of it. We have a few other officers and we'll get some reports on them later on. But not until after we have our guest speaker. So that way, if anybody is just here for that and they want to escape before we do our enlightening business meeting section, we might let them get out of the room. So, but with that, speaker tonight is Dr. Monnier, who earned his Bachelor of Science from Purdue University and his PhD from the University of California, Berkeley. He is also a fellow at Harvard Smithsonian Center for Astrophysics and an at-large member of the European Southern Observatory Scientific Technical Committee. That's a lot. Currently, we are privileged to have him right here at the University of Michigan. John is an expert in optical infrared interferometry and is the instrumentalist responsible for the Michigan Infrared Combiner, a beam combiner that allows all 6 of the telescopes at Georgia State University to work together. John's group was the first to combine 4 or more telescopes in the infrared part of the spectrum. They were the first to image the surfaces of main sequence stars other than the sun, including rapid rotators and very close binaries. Some of you may remember John spoke to us about 6 years ago and has since continued his work in interferometry, but he's taken it to a new dimension in a sense. A hint may be his presentation title, which is an introduction to the STARI Mission, an important step towards space interferometry. With that, please welcome Professor John Monnier.
Well, thanks everyone. Before I start, I wanted to just advertise an important public talk that our department is sponsoring in about a month. March 25th at the Michigan Union. So this is advertising or going to explain the next big thing on the ground is the European Extremely Large Telescope, which will be 39 meters across. And this is actually a picture of its current construction state. So unfortunately, the American large telescopes have been delayed by funding. They don't have anything like this. They may have a hole in the ground where they want to build, but they don't have anything started like in this level. And so this is going to be the first big telescope, next generation telescope since, the Keck Observatory became the biggest telescope in 1993 or so. But there's a special Michigan connection because we are partners in the building and the first light science of some of the instruments on this thing. So the Europeans own the telescope, they're building it, they're paying for it, but we have contributed some money and people to work on instruments which give us early access as part of these teams. So we're very excited. That should come together in about 5 years on the sky. And this is the director of the whole European Southern Observatory. And he's coming and he's been in there for 10 years and he's going to talk about the adventure of getting it funded and getting it started and hopefully getting photons very soon. So I hope you guys can come. I'm really excited. No, it's open as far as I know. Yeah, so it's at the union. Hopefully it's a big enough room. Okay, so I'm going to talk about another type of mission. We hope someday can make a telescope even more powerful than the Extremely Large Telescope, which is by going to even bigger distances. But I really have to first advertise the huge team behind this. So this is the biggest project I've ever led, which also means we have a lot more people contributing. So when I give these talks, I don't list on every single slide, who helped with each slide, but hopefully you can tell from the context and the different specialties that all the different co-Is are bringing to it. So I really just need to highlight first, again, to give everyone credit. Michigan, we're the lead institution, as I'll say more about, in astronomy and in aerospace with Professor James Cutler, which I know some of you know from Peach Mountain. He's trying to raise money to resurrect the big dish there. Georgia Institute of Technology is a key player, as you'll see, on working on the propulsion of our satellites. We have a system engineer at Jet Propulsion Lab. Gautam Vashis, we have Leonid Pogorelnik and students at Rensselaer Polytech in New York. There's a nice, really experienced team in Stanford working on the guidance and navigation software and algorithms. And we have consultants, in particular from MIT, Kerry Cahoy. This is a render of what we hope it will look like in about 4 or 5 years of our system. So let me go through first the motivation for the mission and why we're building it. You know, one of the dreams of astronomers is being able to discover and characterize a planet like the Earth. And although we have found many Earth-like planets around low-mass stars, like M dwarfs, we haven't found any around a sun-like star yet, and we don't have the technology to make actual images of any of them, and to try to find, for instance, signs of life around them, right? Some actual signatures that are undisputable signs of life, not just for just water, for instance, which is great. We'd love to find water, but eventually we want to find, you know, ozone or other more interesting signs of life. And so and here's us showing you a spectrum of what an Earth would look like in the visible and in the infrared. On the left is the visible, and what you see is scattered light off of clouds and the atmosphere. So you can see features of water, again, ozone, carbon dioxide. And on the other side, on the other axis, or the other plot, is what it would look like in the infrared. So in the infrared, the Earth is actually glowing, and it also gives off water, CO2, nitrous oxide, and ozone. So they overlap in some molecules, and they don't in others. Each wavelength has some strengths and weaknesses. Like clouds, for instance, if there's a planet full of clouds, it might make it very hard to see the atmosphere, while the infrared could still see it. So there's like pros and cons to either one. Ideally, we'd like to have both. On a technology point of view, though, the visible has a very big problem, and that is that scattering is much less efficient than emitting. And so in order to see the little Earth, you have to see a point of light that's 10 to the 10 times fainter than the star. So that's, 10 billion times fainter. So that's, a number that's unheard of to try to see something that faint next to something bright. On the other hand, in the infrared, because the planet is glowing at that frequency, it's like best place to look at it, where we get to the most favorable contrast of 1,000,000 to 1, which is already very hard, but you probably can imagine we've measured things 1,000,000 to 1 many times in many different contexts, but 10 billion to 1 is actually very rare to measure anything that good, just because of errors and systematics and problems. So what we want to do is do both. The one that the United States is pursuing right now is the visible solution, trying to measure it in visible light. And when you're in the visible, you can use basically the power of one big telescope, or you try to build a coronagraph to block the star. Now, 10 to the 10, again, is, probably 100,000 times better than has ever been done to date. So it's a big jump. But on paper and in the computers, it's possible. So this is a big goal that was endorsed about 5 years ago in the 2020 Astro Decadal Survey. And NASA is trying to fund the technology right now to do it. So it's not fully funded yet. It's on a technology path for the next 5 years. It's called the Habitable Worlds Observatory. It's expected to be, right now, 20 billion. And since most missions end up costing, 3 to 5 times more than they start, it's a little bit of a worry. So that would be, of course, twice as much as James Webb was eventually. So very expensive mission. The other way to do it is in the mid-infrared, as I said. But in the infrared, because the wavelength of light is longer, you need a proportionally larger telescope to be able to even distinguish the exoplanet from the sun. So that's just due to diffraction. But you don't need as big a telescopes. And so the idea here is that you can potentially do it less expensive because the individual telescopes are already done technology. A few meter telescopes, right? That's relatively cheap now, and you need at least 4 of them. So this price is very rough, but some people have priced it as $2 billion, but it could be higher. But that's just to give you a sense that it's expected to be much less. So why do you want to use interferometry? So I alluded to it already, but you probably know, and if you came to my talk 6 years ago, you definitely know that the resolution of a telescope is limited by diffraction to this formula, that the best resolution and angle you can get is lambda over d. Right, lambda is your wavelength and d is your diameter. So the bigger your telescope, the smaller the angle. But I mentioned that in the infrared, you need to have a 100-meter telescope or a 200-meter telescope to do this. And so you can't do it with a single telescope yet. But you could combine many small telescopes together. That's the idea of interferometry. And so rather than have lambda over d, you basically get the power of lambda over b, where b is your, what we call baseline separation. So that's why one reason we need to do interferometry. Now, just like I said, the Habitable Worlds Observatory has something called coronagraphy. That is a special method of suppressing the starlight on axis and letting the planet through. There's a similar method in interferometry called nulling. And this I want to illustrate it here. So you all know electric, light is a wave. So the light comes in. And so it hits one telescope before the other, I show here. Then it continues on, and then you delay it so that you have a delay line on the right there, that box that balances the time so that when they meet in the center, they have the same time. Now, if they meet at exactly the same time, then the electric fields add up, right? They add in phase, and it's called constructive interference. That's what you want. Now, and except for exoplanets, because in exoplanets, you actually want to get rid of the star. You don't want to have the star. So you actually do a slight twist on it where you add a little extra delay to one, so it's exactly 1/2 wavelength off. So that would mean if you move the delay line, it goes up and down and up and down. And so if you perfectly adjust it, you should get the electric field of one and the peak to be in the trough of the other. They cancel out instead of adding. So that, in principle, in theory, gets rid of 99.99% of the starlight. But the planet, because it's coming at a different angle through your interferometer, then the balance isn't the same. So the planet, you see it, the star, you don't see it. And you can look at it on the sky like this. In a simple interferometer, if you tune it to a particular setting, there's like these dark bands. Any star in a dark band will be blocked. Anything out of the dark band won't be blocked. So you can make it so that you block the star, and the planet is like moving around or whatever, and is sometimes blocked, sometimes not blocked, and you detect it that way. So just a little lesson of nulling interferometry. And so to summarize what technologies you need and why we have to do it this way, I mentioned the first one. In the mid-infrared, it's 10,000 times easier from a contrast perspective. So that's great. But we then have to have a very large telescope, too big to make it, so we have to use interferometry. Step 2. Step 3, we have to go to space because in the infrared, the air is glowing, everything is glowing. So it's 1,000,000 times better in space from the point of view of noise. So another consequence of this line of logic is we have to go to space for sensitivity, and it's millions of times fainter. And then lastly, turbulence is terrible. So we also need to do it to get rid of turbulence, or it messes up your system.
Should your color. Oh, thank you.
Make sure it's on. It is on, I hope. Yeah, it's on. Okay. So anyway, but there's one small detail to our dream here is that no one has even flown any kind of interferometer in space yet. Formation flying, meaning 2 separate telescopes. And so, yes, we have done many of these things individually, but one of the most important parts, how do you fly telescopes apart and combine the light, never been done, even in a small scale. Now, I used to think this was way beyond the budget of what I could contribute to. This was attempted to be done in the 2020s, and they tried to launch a mission to do a test, and it cost something like $300 million. And it got canceled because it was too much. It didn't do any interesting science. It was purely a demonstration of the technology, and it got some money for a while, but eventually got canceled. And so at that point, I was a young faculty. I was like, yeah, this is impossible to fund. It's too impossible. But as you know, there's been a lot of space innovation in the last 20 years, right? There are these new kind of satellites called CubeSats, which I'll talk about, which are small, kind of like Tinker Toys of little cubes that are each 10 by 10 by 10 centimeters. So very small cubes. You can join them together. We have Falcon 9 from SpaceX has reduced the cost of launch by probably a factor of 10 or so. And there have been a lot of pioneers, including Jamie Cutler here in Michigan, who have been pushing this technology. And so something that used to be a little small satellite that would, only work 1 out of 10 times when you launch it, now they're working reliably because there's an ecosystem. There are companies that help. They're stable. These things have been now flown 100 times. So it's really amazing. And so I wrote a paper for the decadal survey called A Realistic Roadmap to Formation Flying Space Interferometry, where I outlined, these dozens of missions that have done some of the steps we need for interferometry. They've done ranging, they've done rendezvous, they've done orbits, they've done lasers between them to map their precision. You may have heard of the LISA gravitational wave interferometer, which is now, since LIGO has now found gravitational waves, now that is a supercharged mission that is now going to fly. Before it was always like waiting around, but now it's on the front burner. So there's so much going on. Still no interferometry, but you can see this list of coming up. There are now radio interferometers that are about to get launched to do interferometry. It's not as hard as optical, of course, where you have to bounce like light, but still, it's a great step. So the Era Vista radio interferometer, Sunrise is actually led out of Michigan, up in CLASP. That's a solar project looking at the sun. Click, and then these are some other close formations. So there's a lot going on in the space, and so when I thought about it again about 5 years ago or so, I said, let's try to do this. And so that's when I started to think about what team. And the core of the team that I built is people at Michigan and then people from this team, Visors. This Visors team, it turns out, is a solar mission that has very similar requirements as my mission that I'm going to talk about. And so I basically poached the propulsion team, the gravitational navigation team, and then do the rest at Michigan. Okay. So that's Visors. And I should say that since even we got funded, which was 2 years ago, a year and a half ago, there's been big advances. So this is a formation flying mission in Europe. Here's a video where you can see it's two big spacecraft. They're not CubeSats. This was a very expensive mission. This is like $300 million mission. This is a serious mission done by the European Space Agency. And it flies 2 spacecraft. I don't know how well you'll be able to see it there, but basically you fly 1 spacecraft in front and the one in back, and it's looking at the sun. And it does a coronagraph, where you block the sun, you want to look at the corona. But by having such a long distance, you can, you can do a much better job than you're trying to stuff it into a single camera. And so I don't have it here, but you can Google Proba 3, and they recently published their first image, which is pretty spectacular. So this mission was still in the lab when I wrote my proposal. This mission, it has demonstrated now some of the things that we were going to be the first to demonstrate, but they demonstrated some of it. Of course, they spent $300 million, and we're going to do it hopefully for 10. So we're going to show how, quote, easy it is, right? That's what we're trying to do. And in addition, as kind of a competitor to us, the Japanese last year approved a mission similar to ours, only slightly more ambitious, where if it's successful, they would be the first to actually measure interference and get fringes. So we'll see how they do, but they are a great competitor for us, and we're friends, and we want, of course, to succeed. But we'll see. We'll see what happens. But it's an exciting time. Let me skip. This is just some of the NASA stuff. Like you have to break down what technologies you're demonstrating. So let me get going to STARI. So STARI stands for Starlight Acquisition. We're going to get the starlight, and reflection. We're going to reflect it to another one. And it says, and the I stands for toward interferometry. So this is not an interferometer. It may look like an interferometer at first, but we don't have the 3. You normally would need 3 spacecraft to do interferometry. You need 2 telescopes, and then you have to bounce them to a combiner. So here we only have 2. But it's meant to demonstrate the hard parts that haven't been done before for interferometry as a pathfinder. So the idea is we're going to bounce the light from one, or receive the light from one, bounce it over to the other, and focus it into a single mode fiber, which is basically proves that you can do interferometry. You can get into a fiber, you can take the fibers and plug them together and do interferometry. That's been done a million times. So I don't need to go through all the details, but we want to fly them between about 25 and 175 meters. So that spans the range. That's interesting. It's going to be in a medium-sized CubeSat. That's this 8U. 8, as you might guess, is 8 times bigger than a 1U. So it's It's a 4x2 of these CubeSats put together. We have a very small mirror. You know, we need to save money. We don't need to do faint stars. We're improving the technology of the linking them together. We're not trying to make a big telescope. That would just add cost and wouldn't really be helpful to the technology. We use differential GPS for centimeter level differential location. I didn't know this until I started this, but you can do space GPS in low Earth orbit very, very well. But to get to less than a centimeter, we are going to use cameras that look at each other, and they have beacons, you know, which is how Proba 3 does it. They have beacons all around it and cameras, and then they just, you know, look at where they are, and they can get their relative orientation at the millimeter level. So that's the plan. I don't need to read all of these, but, you know, we broke it. I thought part of what would be interesting maybe for you guys here is seeing a little bit of how it's done, a little bit how the sausage is made, because we just went through our phase A review after 1 year. And so this is about kind of a grouping of a bunch of the slides and some of our initial documentation. I tried to, of course, not show you all the nitty details, but there's some details in here that are probably overboard. But hopefully you can get a sense of what it's really like. So the what's called the threshold, or the sort of minimum, so-called like kind of easy stuff, is just we're going to just bounce light from one to the other any way possible. We're going to be able to do some orbit control. We're going to go from sort of a safe orbit, which is like really safe, even if you like lose contact, they're never going to hit each other, to our more, I would say it's, you know, you have to be careful. If you're close in, they could bump into each other, right? If you've somehow lost all communication or something like that. So we only stay in that mode for shorter periods of time. And we have extra safeties and stuff like that. So we need to demonstrate that agility. And then we're just going to take a bunch of measurements of the bus of the spacecraft to see how much it vibrates and things like that, which we need for the next step. Vibrations, you know, are very bad for interferometry, because if even a mirror moves at a wavelength of light, you know, tiny amount of vibration can completely destroy your interferometry. So we want to, and you know, because it's never been needed, no one ever measures it. Like, there's no published measurements of this at the level we need. So we need to do it. More advanced is just basically getting the light into the fiber and stabilizing it for an extended period of time. And yeah, doing more of this automated, and also just reducing our error bars. Like at first, we only need to align them at 0.5 meter, and then in the second stage, we're going to do it at like 10 centimeters. You know, so it's a progression of our precision. And then lastly is going to very wide separations, like 200 meters, which is going to be, we're going to have some issues with that, and again, pushing the precision down to a centimeter of error. So we want to control at a centimeter, which is really beyond anything a CubeSat has done. Okay, so I don't want to go through this either, but those goals, those top level science requirements, you know, to do it, you then have to say, well, how can you do that? You then have to, of course, flow it down to subsystem requirements, right? How well do I have to measure that beacon? How well does my GPS have to work? How well do I have to control the pointing of my spacecraft? So anyway, we did that, linking it up. So here's the team. There's James Cutler. Since I know many of you know him, I put him up here. He's the brains and the sort of glue that combines all the system. You know, every single person on this is an engineer but me. So this is a technology demonstrator, so it's engineering. But I'm the scientist who wants it to work so bad. So I had to organize everybody to do it. And I'm building one part, because I build instruments, but I do optics. I don't do the aerospace stuff. So I'm doing one piece of it, the optical part, that looks a lot like what I've done before. So anyway, the bus, organizing the bus and the glue of everything is James. We have, I mentioned guidance at Stanford. I mentioned all this already. Propulsion. Then there's the beam transport with me and Rensselaer. And then they have to talk to each other with a radio link, right? They have to exchange information. That's also James. And we have some help from JPL. Mostly that help is available, like if we really need it. Like if we get in a bind, you know, we can go to JPL and get some really expert help if we find ourselves in trouble in some way. So what's great is this is the first space mission ever led by Astronomy. So there have been many up in engineering, but astronomy never has. We're always part of and that's because most astronomy missions are much more expensive than the ones up in engineering, where those are generally looking at the sun or, looking at the magnetosphere or something very local, and there's a lot more money for that. Or that they don't have to be as big, because in space we need big telescopes, cryogen, it's just way more expensive. So we've had a lot of our professors working on those missions as science advisors, but not leading $100 million project. That's quite hard to do, right? But anyway, so this is our first mission done by astronomy as a leader of it. And again, we have James running the show behind the scenes, making sure it all works. This is an engineer. So, and we are going to do as much at Michigan as possible. So as you'll hear, we're going to buy the big spacecraft. We're going to buy the stuff that has been done before. Like we don't want to we don't want to build everything ourselves if it might be a risk, because we have a lot that has to work. Interferometry is famous that has like 10 things that have to work, and if one doesn't work, the whole thing fails, right? And so I want to make sure we buy down risk when we can. So we're going to buy the bus that has the solar panels, that has the batteries, that has the star tracker, things like that. It has gyroscopes, reaction, all that kind of stuff that you've heard of. That stuff you can buy. And then we're going to receive it, and then we have to integrate all of our pieces into it. And we have a very complicated payload. We have multiple optics, multiple cameras. We have propulsion system, which we're making as a team. So it's a big job. So that'll all be done in North Campus. And we have the clean room. The Space Physics Lab up on North Campus has big test chambers, because they do a lot of satellites up there. You have to vibrate it, really strong before you can put it on a rocket. You got to adjust its temperature over a wide range to make sure it doesn't break. And you got to, of course, bake it out at a vacuum for outgassing and things like that. So there's a lot to do, which none of which I've done, but James has done most of it, luckily. Okay, so getting to operations, again, I'll try to go quick. I mentioned already the idea is we're going to launch it. We're going to have 2 modes, standby mode, science mode. We're in engineering mode, so we don't have to be like 24/7 manning the station, because we're a small team. It's technology only. Once we do our technology, we can turn it off. Like we don't need to run. It's not like astronomy again, where you have to use every second. So we're going to basically do an experiment a week, put it in standby mode, analyze the last week's data, plan the next week of data, send the commands for the automated stuff. Then when it's doing it, we'll try to be there live to monitor it. And then it will go back for a week, and we analyze the data, see what happened. As it takes time to analyze data. And then at the end, we are supposed to deorbit. So this is, I'll mention again, deorbiting is an issue because there's now more strict rules. Because of Starlink and all these commercial enterprises having thousands or tens of thousands or hundreds of thousands of satellites, they're trying to make sure those companies have plans that they don't stay up there more than 5 years once they're over. And so that's affecting us, even though we're just 2, but we have to deal with some rules that are kind of hard for us to deal with, but we have to deal with it. And this is where I'm just trying to share some of the details I think are interesting that I learned along the way as an astronomer. I thought were interesting. So low Earth orbit, 500 to 900 kilometers, say. 500 has a very fast deorbit time of only less than 5 years. But for interferometry tests, it's bad because there's a lot of drag. And so if your spacecraft have different masses or different profiles as they go around the Earth, they'll start to move and have an extra kind of distortion to the orbit. And we really don't want that. So we really want to go up to 800 kilometers. But there, it won't deorbit in 5 years. And so we have to figure this out, at least not easily. We also would like to be in a sun-synchronous orbit. And that means more or less you go over the pole. And ideally, we want it to be what's on the terminator. That's like right going over the day-night boundary. And that's nice because you're stable. You're always illuminated, maximum power from the sun. You look sideways at each other. You don't see the sun. You look away at the star. You don't see the sun. It's just the best for us. However, when we got into it, it turns out only 4% of ride shares, that is when you hitch a ride with with Starlink or something, only 4% are in such orbits. And so it's a risk to our mission if we demand to be on such an orbit. And so we change things so we don't have to be on such an orbit. So that means we go night, we go in the shadow and so cool down, and then we go back in the sun and heat way up, and we have to, and then we might see the sun sideways. So it leads to a lot of complication. Anyway, things I never thought about before we got funded. We're going to use, again, SpaceX. There's multiple groups that use it. One amazing thing is the prices just keeps coming down. So at the bottom here, I show you that the cost to launch these 2 CubeSats is expected to be about $500,000, which is only 5% of the total budget. So it's really not the thing that most matters anymore. Like I said, 10 years ago, mass was everything, and now it's kind of like we're spending 20 times that on people and hardware. So it's like kind of a, no big deal. So anyway, so that's interesting. We're trying to decide, do we launch them connected and then separate? But then what if it doesn't separate? Like, what if something goes wrong? We don't want to have any risk, right? So like, do we really have to be connected and separate and worry something fails? The problem is if you don't do that, they can drift apart. You let them go, and the company lets them go whenever they do, and you can't control it, and they could end up, like literally, after a few days, it could be on opposite sides of the earth. And because there's rules, we learn like little details, like you're not allowed to use any propulsion or deploy anything within the first 7 days. Not to make sure they don't hit each other or whatever, but of course we want to stay close. So we have to look into this. Like can we get back into orbits or not? It's not so easy. Very few people have to worry about this. Okay, so I mentioned this amazing team from Stanford. They're like really the top team in the world that does formation flying. So they're involved in multiple formation flying missions. None quite like this. They're usually way farther apart, like thousands of kilometers or hundreds of kilometers apart. But nonetheless, they have all the software. It's been tested. Like, this is a really big deal. Like, if we had to do all this work from scratch, it would be impossible. So this is like 20 years of their work that we just get to use almost for free. It costs 2 grad students, which is what it costs. So, so they have all this nice graphics too. That's what's nice. They have nice graphics, They make the movies of how they're going around each other. And so, yeah, this is what they do. They make these movies and they figure out how much propulsion we need. They figure out all the details. What's the air bar? I just want to mention this is a cool simulation. So for interferometry, the main thing we care about is that the tube spacecraft are perpendicular to the way you look. Because in interferometry, I mentioned you have to balance the light beam. So that means in space, you want them to be perpendicular to your line of sight so that the light will come in, bounce, and be the same. That's what you ultimately want. So if you want to control while we're going around the Earth, spinning all around, we don't really mind that we're spinning around each other or even that we're going farther and apart from each other. But what we care about is that we're not moving towards or away from the star in an uncontrolled way. So that's our main thing we are trying to control. And this graph shows that error. So this graph you see should be 0. That's what we want it to be. But because we're in the low Earth orbit, there's errors in GPS as well as there's perturbations called J2 from the gravitational field. The Earth is not a perfect sphere, and so as you go around, you get perturbations from the obliqueness of the Earth. So it puts in this oscillation, and if you don't control it, it kind of gets bigger and bigger every orbit, right? But here you see that every red line, you see there's a firing of the propulsion system in the simulation, and so with doing it like once every 60 minutes or so, they can keep it within this boundary. So that's like new stuff that they were able to simulate, for our mission, which is good because that's what we want. And then there are some limitations to how many stars you can look at, but this is another nice simulation by them. Again, they have great tools where they show you all the bright stars that can be observed during the 6 months of operations that we have. So you see the band has to do with where we can observe and change our orbits to observe it, and then the dots are different stars. So just showing you that it's feasible. Phase A study is about feasibility, so this is what we're showing. The cool gas thrusters is a great legacy. Georgia Institute of Technology with Glenn Lightsey has built half a dozen of these on missions. Now, and he's not resting on his laurels. He's improving it this year, so that adds risk, but it also helps us if it works. This cold gas just means it's considered it's not considered, there's a NASA term for it. It's low enough pressure that it's not considered pressurized. So that helps you, like putting on a rocket. Like if it were pressurized and we put it on a ride share, that would be bad, or we'd have to do a lot more work to prove that it's safe. This is considered non-pressurized. It is pressurized, but it's considered a vessel and not a tank. I don't remember. But the point is it's good, it's cheaper, and it's safer. And it's just so, but the basic idea is simple. You have a gas, you pressurize it to the maximum you're allowed to, and then you have nozzles that point in all the directions, and you just open a valve for a short time. You shoot some gas out, and you move. Now it's a little more fancy than that, but that's the basic idea. And the main thing he's going to add is a heater. So if you, and this is just makes sense. If gas is hotter, then it has more pressure, and you can get more thrust out of it, right? So this is showing you thrust versus temperature. Colors are temperature. You can see by heating it up to 50 C, we can get like 4 or 5 times more thrust, which is important for us because we have a lot of things we have to do. It's go from safe orbit to science orbit constantly, and that's a lot of thrust, it turns out. Okay, optics. So the part that I'm most excited about is the optics because that's the part I'm building. And so this has to do with how we're going to get the light into the fiber over 100 meters apart in this dynamic, moving low Earth orbit. And so it's basically split into 2 parts. The first part is we have to get the light over to the other telescope, into a hole, right? It has its own optics. So we have to get the light into ours and hit a moving target. And then that system has to take the light and then do a super precise alignment into a fiber. So we have 2 steps. So we call it the pit and the fid. So the pit is the first part, the pupil transport. The basic idea is that we have a beam splitter, so we look at 2 things simultaneously. If you've ever done optics, you can look through a beam splitter and see your star. It's a half and half beam splitter to simplify it. And the beam splitter looks sideways at the other spacecraft, half, 50%, and it sees beacons, these LEDs. So we're just looking through this, and we're seeing a star, and we're seeing superimposed the 4 beacons, and they're moving around because our spacecraft is jittering and it's moving, and so we just align them with a moving mirror. So we have a mirror in the way that guides them to stay aligned. And so it basically does is the starlight comes, reflects over, and we're like in live real time correcting for all those jitter. So it's funny that because I'm used to doing something like this on the ground, but on the ground, we're the stable one, and the atmosphere is causing it to wobble. Here, the star is the stable one, and our platform is wobbling. So it turns out to be harder. Anyway. So once it gets over there, we have to, I forgot. There's one little problem, again, just little cute stuff, is if you send a light beam over a long distance, it starts to self-interfere, called Fresnel diffraction. And so it spreads. It also gets phase errors across it, which is bad for interferometry. And this just shows you a simulation of how a beam that starts out perfect just gets worse and worse and gets these dark bands. You can do this yourself with a laser if you have a lens. This is like a lab measurement trying to validate our test. So the left is a lab measurement, and the right is like a simulation. So, anyway, just all the details you have to get into, right, when you do it for real. So basically it means it has to be a certain size. This effect is worse when they're very small beams. So it means we can't make the beam too small or this starts to be bad. Okay, once it gets there, what happens? We have to guide it in, and we basically play a similar trick. We have another beam splitter, and we look at the starlight, and it's moving around on the pixel. But this is easier because we don't have to send it out hitting another moving target. It just has to hit a target inside yourself. So you just have to now take that moving target and push it onto 1 pixel, and then it will go in the fiber. So it's an easier problem. What makes it harder is you have to do it like 10 times better, precision-wise. So that makes it harder. But that's the concept. I'll show you more. Now, how do we do it 10 times better? Well, we use something called super centroiding or super resolution. And I don't know if any of you have played with this, but the resolution I mentioned in the past, or in the beginning, lambda over d, is the full width half max. But if you know, and that's the limit of your resolution that we call the resolution. However, if you know what you're looking at is just a point source and it's just blurred, you can measure the center of light much better than the width, right? I mean, obviously you can. And the amount you can is just the full width half max basically divided by your signal to noise ratio, which is related to the number of photons, root number of photons. And so we just calculated that we have to measure it at about 1/10 of a pixel is what we need to do our science. So you see that we have 2 pixels across the full width half max, but we have to do 1/10. And we just did some lab demo. I mean, this is done pretty routinely in astronomy, but we have to demonstrate things. So we did it in the lab. we set up some LEDs and a camera. Here's some real images, and we measured, and we could move it by hand, with a micrometer, and we could measure it to generally about a 40th of a pixel. So again, this isn't that controversial, but we did it. So we have to measure it at that level. And then we have to steer it, I mentioned, to within that level. This just kind of shows some of our more sophisticated calculations with the Fresnel diffraction and everything taken into account, and the way we tried different wavelengths. We had to do it as study. And this just says we need to do it within a few arc seconds to get more than half the light in. We want to do better than that, but that's just minimum. This just shows you if you steer off, the amount of light in the fiber goes down, and you can kind of see the behavior there. And not to go into, I already explained it, I think, but just to show you, we prototyped that too. So we have a little telescope 1 on the left, and then it's looking out at those beacons, and then there we take the light and we observe where it is, and we send it into the fiber over here. And one cute trick is, what are you going to do with the light in the fiber, right? Originally, we had a special subsystem with a photodiode and stuff. But in the end, we realized, no, why don't we just use that camera? That camera has 2,000 by 2,000 pixels. It's not doing much. So we just take that light and bring it back around to the fiber and just put it back in the camera somewhere else, doesn't interfere with the star. So that just saves us a subsystem, and it's kind of smart. And it works, just to say. Here shows you what it looks like. You got 4 circles. Those are our beacons, the green ones, right? And you see a little star in the center. And once you align it, you can check, since it's in the lab, that it works. And then here is where next screen is where I show you, that is the image on the other camera where we just see the star. It's there at the bottom. And if we adjust it perfectly to the right pixel, then it should go in the fiber. And then up at the top is then you see the other light. Again, it's hard to see here because it's very small dots, but it actually does work. In the lab at least. Okay, so great. So we're prototyping. And eventually we are working on a simulation. We like to prototype things, but we can't prototype everything. We can't put in realistic errors of the jitter and the errors in the spacecraft formation. So we have to also validate with simulations. And so this is still in early days. We haven't done a very good simulation yet, but here you can see on the left kind of what you just saw. You see 4 dots and the star in the center. That's what the first camera sees. And the right is showing you, does the light hit your other telescope? So here you're seeing right now, they're not aligned. On the left, you see the star is not in the center of the 4 dots. So it's when it hits the other telescope on the right, you see the circle is what you need to hit, and it's missing. So we need to add in the feedback loops, add in the controllable mirrors, and show that we can do it. We can adjust the signal to noise ratio, et cetera, with the simulation. So this is really important in the next year as we get to the preliminary and critical design review to show that this works. Fitting in it is not easy. Originally, we were going to fit it in this geometry. The light comes in that long edge and goes out the small end. But when we actually laid out the beams, it was really a train wreck, a train yard. I don't know. You see that? How many mirrors and folds to fit within that volume? Which, does work, but it's a lot of hardware and it's a lot of things that might drift or go out of alignment. So we rotated it 90 degrees like this, and now things lay out way nicer. So now we just send these beams. These beams can now just go along the length and not have to get, folded 3 times to fit within the volume. So, as you can see, this is tough. All right. The last bit about here is the bus. So the bus is the biggest single item in the budget. The 2 buses. So this is a big ordeal with non-disclosure agreements and requests for information and quotes, and it took a year. At the end of the day, we got a lot of quotes and a lot of different prices. So the quotes were as cheap as around 1.9 million for 2 to 5 million. So really big range. Now our budget that we put in the original budget, which was an estimate, was 2.1 million. So only one was within our budget. Now that doesn't mean NASA wouldn't have helped us pay for more if needed, because prices change and they recognize you're estimating things and things can change. Indeed, all the pricing went way up. Some of these companies went from 2 million to 5 million in 2 years, like ridiculous. So anyway, that's the way. So yeah, so the upshot is we think we have it. It's not official yet. We're going to meet with NASA next week to tell them our choice. They ultimately could veto it if they want, say, no, we don't like that company or whatever. So we'll see. But I'm pretty happy with it. Now, one little wrinkle in our risk chart is, tariffs. So turns out this company we like the most is in the EU. So an extra 15% on 1.9 million is not nothing, right? So that's many hundreds of thousands, $200,000 or something, right? So that's a bit of a problem in our budget, but we'll see. There may be ways we can get it waived. We're not sure. Didn't something happen today in the news? Didn't the tariffs get thrown out? So I don't know. Maybe it's safe. So, huh?
Supreme Court outlawed.
Yeah, outlawed it, but he said he's going to do it anyway. So I don't know. Who knows?
Who's sworn to?
I'm learning as a PI, I have to worry about everything, much more than my smaller projects. I want to, one last, I guess we don't have, well, almost done. You've heard of probably you may have heard of lots of the issues with space. There's energy, there's power budget, like how big are your solar panels, there's how big your batteries are in case you lose your power for a while, like you're in the shadow. There's hard drive space, all this stuff, right? Downlink, like how much data do you have? There's thermal budgets, like because you have to, all your things have to work within a huge range of temperature because you can't control that sometimes. There's the mass. But one that came up specifically for us, which is unusual, is what they call the delta V budget. So V is velocity. And every time you use propulsion, right, your goal is to change your velocity. And it turns out, if you know your mass of what you have, of your spacecraft, then, if you have a thrust, that's a velocity change. And so you can express your amount of propellant as delta V instead of kilograms or whatever. And so we have to track our so-called delta V budget, and it's all I hear about. All the delta V budget. Like the Stanford people are really good at this, and like they make all these tables simulating our delta V budget, because every time you go from here to there, you got to use delta V. Every time you want to find your delta V, you got to go into an emergency mode because there was a solar flare, and you reset everything, and you go into safe mode, delta V. So like we just have to do all this delta V. And ideally, we'd like to have enough delta V to deorbit, which we really don't, but we would like to. So we have to just track all of that. Anyway, something I didn't know about. And if you're interested in the number, if you have a gas tank about this big, you can get your spacecraft moving. If you blew it all at once at maximum thrust, you could get to going about 14 meters per second. Like you use it all at once. So we talk about it in meters per second, which I just think is kind of cool. So we have 14 meters per second per spacecraft. All right, so getting near the end here, what are the milestones? So we started last year with NASA APRA. That's the Astrophysics and Research, Astrophysics, what is it? Astrophysics Research and Analysis, I think. Research and Astrophysics, blah. So far, so good in terms of funding. There's a lot of problems at NASA funding and things being stopped and all this stuff, but so far it's been fine. We passed there's three required reviews you have to go through. Required meaning there's external people and NASA watching and checking everything. We'll do lots of internal reviews, but we have to have three really real reviews. And that's very light. Most NASA missions have, 100. I mean, I don't know, so many, right? We only have a few because it's the cheapest type of mission. We had our first one last December, which we passed, although we had to do some things. We're in phase B, which is now the design phase. So in a year from January, we need to do the design review, which is basically saying we have checked everything. We have an actual design. We have full CAD. We have the true budgets now of everything that we want to buy, everything, and it all adds up and it all works. And no one found any problems in our previous assumptions. Then we have a year to build it. Subsystems while the company's building their part. Then at the end of year 3, everything comes to Michigan. So the goal is everything's here January 2028. And then we have a year to integrate it and test it. Like shake it, that kind of test, environmental test it. And then end of that year, we need to have our required flight readiness review. And then 6 months later, our launch. And then we have 6 months science mission. So even though 5 years at first sounded like way too long, like, 5 years, that's so long. Because everything I've done is 3 years. Everything I already built is 3 years. So like 5 years seems like forever. But you can see, it actually it's gonna be a year of this, a year, and yeah, it's gonna go quick, I'm sure. So I just want to thank again the team. This is everyone who came to Michigan last May for our first kickoff meeting. We're having another in-person meeting this May and Rensselaer. I'm looking forward to seeing all them again. And thank you so much. And stay tuned.
Questions for John?
Yeah, question? Yeah.
So a few things that I'm going to do all at once. One is your Google mirror.
Yeah.
Gonna make the whole thing vibrate.
Well, it's moving very small amount. But you're right. Every time we do a propulsion, these are off center, like the reaction wheels are not center of mass. I mean, yeah, there's going to be parasitic torques, they call it, every time something moves. Yeah. I haven't considered that one particularly just because I assumed it's really small, but I've been worrying more about the reaction wheels, which have to spin the whole spacecraft, but yeah. Yeah, that's right. So I didn't mention that, but the camera is running at 50 hertz, so we'll have about a 5 hertz control bandwidth, so not super fast. So order 10 arc seconds, 5 times a second. So I hope it's not much. But no, I always have to work, since I don't do space generally, I'm learning every week. I think of some other possible problem, yeah.
I mean, you're working at the micron dimensions to hit the fiber.
Right, yeah.
So single mode fiber is tiny.
Yeah, so we're moving it like 10 microns or so edge to edge. A few times a second, so I think it's not a lot of work, yeah.
So it's important that your
Baseline, yeah.
is exactly perpendicular to your line
Yeah.
of sight. The distance between is so important.
Right, yeah.
So from a technology demonstration perspective, that's true. From an interferometric perspective, you gotta get that baseline accurate to the micron level.
Right, that's true, yeah.
Yeah.
So one reason is that direction, we have other technologies to measure. We can bounce a laser back and forth. It's been done many times on other NASA missions, so we didn't test it here. You can bounce a laser retroreflector back, interfere it, and measure that as well as you want to the sub-nanometer. That's what Lisa's doing. So yeah, so that part I'm not that worried about because we can measure it later if we need it.
Well, for that experiment, you need to control the separation to that level or simply know what it is at every point.
Good question. So in a future interferometer, there will be what's called a differential delay line. So inside the combiner, there will be a delay line that can maybe move like this far. So this part I talked about, we're moving like this and we're only controlling it to 0.5 meter or point. That's driven by the fact that we can put a 0.5 meter delay line inside the future combiner. So we don't, but we need to have knowledge, but we don't need to control it. Yeah. And in fact, this part's hard. The only way to have knowledge in this direction is actually to look at a star that's bright enough to see it. Or maybe some fancy LISA-related technology where you can do super accelerometer type stuff. That's TBD. Yeah. But no, that's a good question. Yeah, the future, we've assumed certain technologies that we can use in the next stage that we're not testing yet.
Looks fun.
So yeah, so our goal is to show that if a university-based groups, right, can do this thing that people thought was way too hard, that has sort of blocked interferometry missions. Because you want to apply for an interferometry mission, it costs $500 million because you need to tell, you have to do science, you're not just a stunt. And then you say, oh, well, that sounds great, but no one's ever done that before, and what if it doesn't work and it's so risky? So that's kind of like always holds it back because people just think it's too risky. And we're trying to show, look, it's not that risky. Put some beacons and some mirrors. I mean, you're just bouncing light between two things. It's not actually that risky. So I just said, I'm just going to do it. Like if people think it's risky, we're going to try to do it. Right? Of course, if it doesn't work, we'll blame the budget was too small. But if it works, it'll be a very strong statement that it's easy, right? That's the thing. Well, Proba 3 did it for $300 million. So they have now shown it can be done. And so we just have to do it for 10 million. Yeah. Uh-huh.
What is the thorniest problem you think you have to resolve before you can get this thing in space?
Well, one of the biggest risk right now is that the star tracker jitter is not measured by anybody. So we have very few on-orbit measurements of how bad it is and how fast it is. So that's my biggest worry. And the fast steering mirror hopefully has a lot of strength. Since we don't have to go to faint objects, we can look at so let's say we have something really bright, so we can get a very good measurement and track it even if it's pretty fast. So that's my biggest risk. Technical risk that I just don't know why we can't get data on this, but most missions just don't.
Space-based, I know, balloon-based observatories, have a lot of jitter issues that they have to resolve. Could that provide any reasonably, data that you can work from?
I mean, obviously it's a very different environment, so I don't know. I'm sure they must do what we're doing, some star tracker, some sort of fast mirror to fix it. Yeah. Usually,
And I don't think that the jitter rates would be comparable.
On a balloon?
Well, there's something that's hanging on a string that's doing this. The balloon, it's the platform that's wiggling.
Yeah, I'm sure it's quite different. So I don't know, but there may be technologies in common, but the actual amount is not the same. Yeah.
I was a little bit curious because you showed a video on one of your slides of like a simulation of the optics. And it was jittering all over the place. Is the amount of jitter in that simulation more or less just a wild guess how much jitter you're gonna get, or?
So it's the amount of jitter that they say that they would guarantee. So they guarantee like 1 arc minute of jitter, which is way too much to like hit the work. But the problem is it doesn't have a time scale. So they'll say we can track something within 1 arc minute, but they don't say about how fast does it change 1 arc minute. They will not tell you that, and they don't have any data for that. But every measurement that's been done of something similar I have found has been slow. Like it changes in more than a second. It takes more than a second to shift that much. Now,
So you got time to react.
yeah, we have plenty of time to react. Yeah. So there's been some measurements of a different system, a different star tracker system that there's only been one mission that they've actually measured it, but it's not the same bus company as us. But it shows something. And the other one is the exact same bus company, but it was measured in the lab. So they put it on an air bearing, so it floated on air, and then they bounced the laser off of it and they measured it. And there it was very good. It was only a few arc seconds of jitter. So the thought is that the slow jitter is mostly coming from thermal variations. So there's very strong thermal variations, right? One side is 150 Celsius and the other's minus 50 or whatever. I don't know how extreme, but it gets extreme. And so the whole system is straining and bending, and so something over here and something over here is having definitely an arc minute of error. So that's the thinking. I mean, that's my theory. My operating theory is coming from temperature gradients that are highly variable in low Earth orbit. But I don't know for sure. There's resonances, I should say. One danger is resonances. So if it has resonance, it can can build up. So a small signal can get amplified. And that's a big worry because that can be very fast. The resonant frequencies are hundreds of hertz. So if that happens, we're in trouble. So we'll try to measure the resonance frequency. You can try to design put things in it so it doesn't have obvious resonant modes, try to pick up the modes, stuff like that. But that's a TBD also.
Right. So this is primarily a technology demonstration.
100% technology demonstrator. No science that we've thought of that we could do with this. If we could think of some science to do with the cameras or whatever, we could. But it's a 1-inch aperture. Not a particularly big camera.
So just on interferometry, why can't you do it like take a picture here, take a picture here? The differences between the two, and then do it land-based in a supercomputer or something like that. And call it convection.
Well, there are some technologies that are similar to that. So, like in the radio, you can do that. You can record the electric field directly. So the issue is you have to interfere the electric fields. So once you've detected it as photons, it's the electric field, the phase is lost. And so simply put, you can't do it if you just take photons. Now there's something called intensity interferometry, which uses some quantum effects that can work, but it's very insensitive. It works with super bright things, so it's not good with like a small telescope. Like if you had a 10-meter telescope, you could do that in space, but or there are quantum methods that we're exploring that you could try to think of how you would send a quantum resource to your 2 telescopes, or there's futuristic quantum hard drives where you take a photon and you put it into a quantum hard drive, and then you bring the quantum hard drives together and then interfere them after the fact. So like that's a dream that people write papers about, but it's decades away. So yeah, it's just that they're just too we don't know of a way to do that because you have to keep the phase information.
If everything works perfectly, how far apart will that
No, definitely. Yeah, I'd be curious to know what we can do. I'm sure we'll try to do it, see how far we can go. The problem is it will start spreading out. That Fresnel diffraction, that will limit the sensitivity. And so we can just go to very bright stars. So 200 meters should be fine for, magnitude 2.5. You guys know magnitudes. I don't have to avoid saying that. So 2 magnitude, our specs are all for V2.5 for doing all of our work. But, there's a few stars brighter than that, 10 times brighter. So we could go probably... I don't know, 500 meters. I don't know if we could get to a kilometer, but at some point we can't aim, or we'll get lucky, like it'll be missing half the time, but every once in a while it will go through and you'll see a bright, you'll see it. So, depends what you mean by do it. Like if we can just get lucky, wait around for it to happen to work, maybe.
They're experiencing a moment and then so you can just keep going up and up for that 1 week.
Yeah, we could just keep trying. Yeah, we could just try longer. Oh, we did. Let's go longer. Yeah. Yeah, for sure. I'm sure if we have time, we'll do that. Yeah.
Meters is what is the first goal. That's the
100 meters is the sort of the one we signed up for as a requirement. So 200 is the stretch goal. Okay. So we definitely will lose light. 200 meters, we will be losing half the light or something. So it starts to be great.
Do you have to include deorbit in your budget?
So this is a sticky point because yes, we're supposed to. But so far, NASA has given all the small science missions waivers, or FCC has given all the small missions waivers. So it's a touchy point because NASA is actually telling us, oh, don't worry about it that much. They're always giving waivers. But the problem is the way it works, it's FCC, it turns out, is who does this, who does the communication. So if you fly, like if we had our European partner actually do the flying, then we don't have to go through FCC. We don't have to meet this deorbit requirement. It's only the U.S. requirement. So, so the question is, what do we do? I think we're going to have to carry some emergency procedure if we don't get a waiver. That's basically this question. And you can't get the waiver or you can't apply for the waiver until you get manifested on a rocket. So you can't do it like now. So can I have a waiver for 2 years from now? No, you can't. In 2 years, you can ask for a waiver. Like months before you have to get on the rocket. So it's sort of as a PI, I'm like, So I think we're going to say we'll take out a camera and we'll put in more propellant, or we'll have to launch to 500 kilometers and not 800 kilometers. It's like those kind of huge, we'll have to do something dramatic like that. I don't think we can really. We don't have enough propellant to do it. It takes basically that 14 meters per second is what you need to deorbit, pretty much.
Okay.
So it's possible if we doubled if we have space, we could just double if it turns out we have space, we could double the propellant, but we don't have the space as far as I know, Yeah, lots of these rules, like this, and I didn't know any of this complexity, when I wrote the proposal. So it's definitely adding to my stress.
Another question.
Uh-huh.
Are you about to do all the certifications here? Or does you have to send it away and ask them?
No, we can do it. I don't know the details how it works. It's really the rocket companies that care. So you're sharing a ride with a lot of other things, right? And they are the ones that require the documentation that it won't vibrate into 10,000 pieces when they launch it and destroy everyone else, that it won't outgas and contaminate all the other rockets. All these things are all about, I think the people that care are the rocket people who you're sharing with. And so I haven't learned how they verify. I have no idea any of that. But I just know that somehow, I just heard the stories of, if you, this conjoining, I talk about conjoining them. So they said, I just learned that if you shake one, shake the other, hook them together, that doesn't count. So then you'd have to reshake them both. So there's all these rules, and I'm like, who checks that? Like, huh? You have to videotape it. Is it you sign an affidavit? I don't know. I just don't know. So, or do you hire a third party? I just don't know. So yeah, good question. There's a lot of things I don't know yet. I know it's done. I know they do it here. It's just since I'm not an aerospace person, I haven't figured that one out yet. That was great questions, and I had many of those same questions.
We have any questions from the Zoom audience?
And I'm here if you want to email me. I'm local, so I hope you can stay, stay whatever, stay involved or whatever. Or look out on my website. There's a website, starimission.space, that we hope to keep semi updated. If you want to keep an eye on what we're doing for the first Michigan astronomy mission. Is that good?
Questions from Zoom?
Zoom?
I don't see anything.
No? Okay, thanks again, John.
It's nice to see you.
Did we give you a T-shirt or?
Yes, you
hat?
did. Yes.
Would you like a hat this time, or we could get you a gift certificate?
I have a lot of
Gift certificate?
gift certificate.
Yeah, okay, we'll do that. Send me a mailing address. You might want to me.
All right.
We'll fix
Thank
you
you
up.
so much.
Thank you, appreciate it. Okay. Oh, that's a good point.
Yeah, you're working there?
We're traveling to infinity.
Yeah, eventually you'll get there.
John? So that's pretty cool. Maybe see how far it goes.
That is us like traveling back to time. You spent time deep down in the early days.
Sharing your screen. So that means we're gonna come back, to keep on going.
Everybody in this room is gonna get a bunch of emails.
Oh, yeah. Got rid of quite a few of us in this back before these long.
Yeah.
So probably sharing the screen on what's showing.
Yeah.
He's got to stop the
Matthew
share over
West
there.
is all the way down there.
There you go. Maybe, we don't know what that other video feed's doing, we're just looking at one thing. It's something over there. What did you change the video source to? Can you change, is it set the video source to the camera?
Yeah, for room PC.
Not room PC, room.
Oh. No.
C is what you don't want.
How about that?
Oh.
Can't you get to solution? There's something that does the room itself.
Yeah,
Right?
I just,
I thought that was through that board here.
it's camera one,
Is it 3?
yeah, the front camera probably help too. I don't see it.
No. I didn't change it.
So it's the video source down at the bottom. If you're gonna change that, I'm not sure.
Well, it was on content, now they switched on camera.
Jump, that's you.
I don't know, so how do you get the input from the room? That's.
Yeah, no, so, where'd it go?
You don't wanna share. It's a video. Nice. So is something gonna transfer to room? Oh, no, that's a Zoom.
See, that's that.
That's gonna change that.
See, I think we're supposed to be in there, but this doesn't seem to be working.
That's not good.
Yeah.
Yeah, it's like the cameras. Is that right?
Well, normally they can show the ring.
Yeah.
Either that one or that, or one of those. You'd rather show the speaker or.
Right.
It doesn't seem like those cameras were available.
No, apparently not.
They're supposed to be.
There you go. Right here, maybe?
Yeah. Be big. Let's turn the video.
There you go.
That's Charlie.
Thanks, Charlotte.
I'm at them.
Yeah.
I'll do it in a minute. Okay.
Background for right in.
Okay. I'll go ahead and go through a couple things quickly here. Back on, what was it, January 26th, we actually held an officers meeting. Biggest things that really came out of that is we had decided that it was time to raise the limit on how much we can spend without asking for a vote of the entire membership. This really got prompted when we realized last July that if we had combined the amount that Norb spent and I spent for all the food and stuff for the meeting over at EMU, we would have gone over that limit. So inflation, things like that. So we talked about it. We decided whatever we do should carry us a few years into the future so we don't have to do this all the time. So we came up with $500. According to the bylaws, that has to be noticed via email and the newsletter at least 1 month before we take the vote. So because of the newsletter delay and everything, that pushes the vote until March. Meanwhile, people were able to email votes. The bylaws don't really say when they can start emailing those votes, so of course they started immediately. I just made a little folder, been collecting them there for the count. I think we've got maybe 25 or so in there. They were all yes. So anyway, we'll be doing that next month. Another one is we talked quite a bit about the club purchasing an image intensifier. Brian Odom had brought that up at, I think it was the last meeting. If anybody's ever seen these devices, they're just kind of like a small, I'd like to say telescope, but they actually don't magnify. They're just a one power thing. They just make things brighter. But if anybody's never looked at the night sky with one of these, it is an amazing experience. Absolutely amazing. So we got thinking this would be a really cool outreach tool for different events we do, like the open houses, some of the places we go. But there's a lot to think about in this, like security issues. We don't want it dropped. We don't want it walking away somehow, because these things are well over $4,000. That does not include a nebula filter, nor does it include a 55 millimeter Teleview Plossel eyepiece, which it does fit onto. You start throwing those in there, and now you're looking at well over $5,000. On the other hand, technically the club can afford it. So what we decided is let's just chill for a moment. Brian is going to bring this thing to as many open houses as he can make. I encourage everybody that's curious, please make it out to one so you can actually see what this thing does.
and just see if we still have the same opinion, if this is really worth it. We do know that was either the Ford or the Warren Club, I believe. Ford, yes, they bought one, and from what I understand, it's been an incredible public outreach thing for them. So the officers decided that unless somehow we get turned off against it, that we did actually approve doing it. But again, pending review, I suppose I would say. So stand by for that one. But again, I encourage anybody, if you haven't checked one of these out, you should do it, because it's amazing to look through this and see nebula and things like that. It's just amazing.
Right, the other risk is that it can be damaged by pointing it at something bright.
Yes.
Point it at a street light, it would.
Yeah.
Optics.
Yeah. Yeah. There's a lot to consider. It was interesting.
It'd be an awesome toy.
Yeah.
Awesome thing to look. You wouldn't view unlike anything else.
Oh yeah, yeah. It's an experience. Brian came up with one interesting idea that probably would be effective to keep it from walking someplace, and that is that whoever happens to be the guardian of this thing at the time, that it would actually be tethered with a dog leash with a loop big enough that they could put it around that person's neck. So if they drop it, it would be long enough, you'd be close enough to the person, it won't make it to the ground. And if they try to take off with it, well, they just kidnapped you too. And if you're bigger than them, they're not going very far. So anyway, there's lots to think about on that. So let's see here.
Please come out, we'll take a look at it.
Yeah.
That's future open house.
Yes, yep. A couple of other things, we did come up with dates for Michigan Math and Science Scholars. We are being asked to do 3 sessions this year. And what we came up with that is June 23rd with a rain date of the 25th, July 14th and a rain date of the 16th, and July 21st with a rain date of the 23rd.
So it's the
June 23, 25,
through 12, and then
July 14 and 16,
20.
and July 21 and 23. That second one, of course, being the rain date in every case. So we'll see how that goes. And we did hear from our friends at Owasso Airport, and we have set our visit up there for August 29th, the last Saturday in August. I'll be sending out some emails about that, and then, of course, going after people to help us out as we get closer to them. And I believe that's all I had. So I will go to Ken. Thanks for taking the minutes, too.
We went to New York City, went to the Hayden Planetarium, bought a box of gift cards. Went to the
Hayden Planetarium in New York City and bought a box of gift cards. They're blank, but that way we can sign one of these and give it to a speaker that doesn't want a monetary compensation or shirt, t-shirt. So it's like David Levy. We could write a card saying thank you, or Fred Adams turned down an offer of anything. So there's a card that circulated earlier. So I've got a stack of these. We can go through these. Cool. My wife submitted the events for the Observer. I think that's about the extent of it at the moment. So that's pretty much all my report.
Thank you, Ken. Don.
Yeah, report.
Two things. The first is I had printed up 200 of these brochures that we can hand out.
Go around if you can. Go around online and see.
I'm sorry, what are you suggesting?
Go around to that computer, the people online can see you.
Really, what do I do? So you want me to come here?
Oh, that I could have flipped it. Why don't I flip it the other way?
So, okay.
Going for.
Well, but then I want to from the side.
Well, then everybody can see the audience.
No, it won't. Not with the background thing. No.
Oh,
They'll just.
So here's the brochure. We have 200 of them printed. What I will
there's a box of brochures to the meetings every week until they run out. I suggest members take as many as you think you can distribute to your family, to your friends. So have a few on your person that you can hand to people who start asking you about astronomy. And some people have libraries and things they'd like to take a few to. So please feel free to take as many as you think you can use.
We have a hold of those in the observatory, so did you get some, Jack?
Jack, you
To
could
put in the observatory?
Yeah.
Okay, cool.
So that's the thing with brochures. And the next thing I just would offer is, there's gonna be a neat planetary alignment next week. Fridays will be the optimum date. And we're going to have above, in the evening above the horizon, Mercury and Venus. And invisible will be Jupiter, Saturn, Uranus, and Neptune. So it's an unusual alignment. So I will send out, I will either be at Independence Park, or in looking at the forecast, we got a bunch of crappy weather coming in. But right now, the forecast is clear for Friday night, which is an afternoon. So if, if later in the week, Thursday or Friday or something, I can spot a clear night, I'll send out an email inviting people to come either to Leslie Park or Independence Park, depending on what people prefer, if I get some feedback. And I'll bring out my 10-inch, and people can, with their own eyes, look at Mercury and see the phases of Mercury and Venus and that sort of thing. So I'll try and make that happen in the next.
Thank you, John. Let's take it on.
So next Friday?
Yeah, Friday the 27th is the best date according to sources.
When you say Leslie Park, you mean like where we saw the transit?
I gotta use your.
Yeah, that's what when you mean up.
To see Mercury, we need a decent western horizon.
Yes, so that's why I was thinking Leslie Park, we can get on the hill that we have.
Yeah, the toboggan hill.
Or Independence Park has got a real low.
Yeah, that might be a better show.
So I've done Independence Park 3 or 4 times last year.
Just don't walk around, Jack.
Probably what I'll do is.
It's got fire.
Turn on the document camera. So this first. Then up there to look. That is your logo.
I know, thank you.
Thank you.
Nicely done. Hey Kathy, nicely done.
Oh, wow.
Well,
There we go. Yeah. There's a focus.
Focus?
Yeah.
Should be a button that says AF.
Yeah.
Oh, there it is, yeah.
But he also has, but not now, there we go. Oh, temperature chart, huh?
Quick look. Okay. I'll explain to everybody what we're doing here. The data here you're looking at comes from the Peach Mountain Observatory. We have a data logger there measuring temperature. And the blue line is humidity, red line is temp, that's when you want to watch, and the dew point is the green line. Now, just for everybody's, so you understand what's going on down here, these numbers here are minus, like a -1 temperature, -17, -21, 4, 9, 6, 8, etc. You can read that. The object of this was looking at the temperature inside the observatory because, as you know, over the years, we bought 2 heaters. One that's on the north wall, one is on the south wall. We've been wondering how well they work. Well, this week in January was a lot of zero weather. And I went out there and got the data from it, plotted it, and it looks like we were up about between the 20 and 30s, and sometimes maybe right at the 30, going back up. And then when I was out there taking this data in those days, observatory still looked nice, and the walls where the heaters were at, those were around 43 to 45 degrees. So they're helping out, but as most of you know, it is a cinder block building with no kind of insulation, and it's a metal roof with no insulation. So yeah, there just comes in and goes out and stays cold, but this helps a lot.
Where temperature sensor?
Now the data logger is in the observatory, but these temperatures come, and I was going to get to that. It's a good question. Very good. See if that still looks sharp. Okay. Our data is taken here. It's about a mile and a quarter.
Is the temperature sensor that you're logging on the McMath telescope, or is it just someplace in the middle of the room? Where are you measuring?
The data logger is off the McMath telescope.
So it's sitting
In the
out
center of the room, of the observatory.
the center of the.
Yeah. Yeah. Oh, okay. Why is that not?
It's in my screen, but my laptop.
Here it is.
Oh, that's right, I'm looking at the wrong screen, darn it.
Okay, here we go. But anyway, this is how I get the data. It's from Cam Dix, and it's through
Weather.
Weather Underground is the one that's actually through. And this is one of their data points out here where they take all their data for their temperatures and that. And that's probably about a mile, say a mile and a half from the observatory. The reason I wanted that is because the other temperatures you can get, but if you look at them, they come from Howell Howell Airspace, and the other one's the Ann Arbor. And those are 20, 30 miles away. I want something close, so I found this, and that's what we use. Okay, so the heaters that we bought and everything seem to be helping, and they seem to be keeping at zero temperature for freezing the place up. Second question, or second project we had, as some of you might remember, last year in October, we get this to show the whole. Yeah, okay. Okay, just for let you know, these guys here, these are the batteries. Now you're looking at the 17.5-inch McMath telescope.
Not McMath.
Pardon me. Well, yeah, 17.5 Lowbrow telescope. Yeah. And right now, this is where the mirror sits. Then underneath the mirror is the batteries. We've been looking at that and working on them. And found out some of those batteries aren't as well. We're going to have a meeting here to get together, take the measurements, order replacement batteries, and get that up to date, get everything. And this is something, as you may know, that over the years we've had different projects we've done with the 17.5-inch just to keep it functional. We could use it in that. I thought that would be of interest, so we're going to work on that. The other one of interest I got to bring up is early in the year, there was a big discussion about, well, let me show you why first. Let's look at this. Okay, as you can see from this, you can tell this is the stairway, this is the step coming out of the observatory. This is all concrete. Then this is just gravel, and it all goes downward. All right. The argument is, over the years, it's gotten harder and harder to push the 17.5-inch out of the observatory. And there's also been a discussion about putting up some type of, we'll call it a portable wheelchair ramp, only because that's what a lot of this stuff is identified as or referred to as. They vary. The reason we're looking at something like that is so you could roll the telescope down, and then it would help some of the people that are walking with a cane or in a wheelchair at times, would help them to get into the observatory a lot better. Now, there's a lot of this that you can look at and go through. The reason I looked at some of this, some of these are modular. You buy the sections that you need, which is fine. And I'm looking something that says maybe we're like less than 7 feet long from the concrete from the observatory door down to the ground area. Now, like I said, this varies. These are different types. We're looking at something like this. It was modular. The prices vary. And there are other places in the area that sell different types of these types of assemblies. So there's one out in Plymouth, Michigan. There's a big one out in Ann Arbor. There's a couple of them that are called discount sales companies that will sell you these at a discount. You order them. The trick is we have to figure out exactly what we want and how big or how long of a piece. And then the other thing is making sure it is modular, because we have to be able to disassemble it. And then from maybe, say, November through March, it'll sit in the observatory. And then around March, April, when we start our open houses, we'll pull it back and be able to set it up. So, yeah, go ahead.
You think that from March to November, it ain't gonna go bye-bye or get busticated or?
Being get stolen? Yeah. Well, that's a thing we talked about before, and we talked about the Wi-Fi connection, which never really happened out there for the cameras and that. So, yes, go ahead.
I guess one question is it light enough that it can be rolled out at the beginning of an observatory, open house? Take it back down inside, that's good consideration. The other is whether you really care or not. The ADA requirement for a ramp is a slope of no more than 1 inch.
The ADA requirement, wait a minute. There is site ramp evaluation for ADA. Yes. So this is why I was thinking about from these commercial guys that sell these, because they're supposed to be ADA compliant. That's what they're supposed to be.
If it's a small level ramp.
And it's not above the ground.
Depends on how long it is.
Right. That's true, because there's a guidance slope for this. And there's also another measure of total rise figure for this, depending on it. So yes, we take those, and I looked how the ground goes down already. So we can look at that and say if it's gotta be a 14.5 degree for every 3 inches of rise or whatever, we could measure that slope and then do it that way. But yes, that is very true. There is a whole list for that to do.
Go back to the picture of the entrance.
Entrance, okay. Wait a minute. I got a couple of those. This might be a better, well, okay. Here's with the one I showed you, but I'll look at that one for a second.
Be a slope.
Yeah, because here's the other part. Gives you a little bit of an idea of where we're coming in here. Okay. And then you can see here that it's 83 inches here. If we want, we might just run to the bottom, because cars do come through there. I'm looking at now maybe 6 feet instead of 7 feet, bringing it back in here another foot. And that may be all we need to have. Now, some of the things I showed in there were 10 foot long. Well, I'm not saying we need that, but you can buy them in sections. And there's a couple of them that were modular, and you buy sections on assembly.
It's more than just to make a solid surface there instead of that crap.
Okay, just getting for cement and expand it.
Yeah.
Well, there's a lot of rock in there, and you could, as I did some years ago, just to hold the rock together and make it even. If we did go in and pull in and do that whole thing as cement, we would have to dig it out. We have to bring in at least something to mix all the cement correctly, not none of this crap they use with the sand and cement when they mix all the extra sand and cut the price down and everything. It has to be something really solid continuously through. So there might be something there.
Change the grade.
Yeah, that's true. You would change the grate, and then you might have a
section on the bottom where it might be an inch or two high going down or something, or go right into the ground, fully level into the ground and do it that way too.
I think, you know, the step is probably about the same height as the field outside. So if we just like went out there with some shovels and some wheelbarrows, we could probably move dirt to level that out. You can put some steps where gravel is. You know, because it would just be we just fill in the dirt. It would just make the whole thing level. And that would mean that you can wheel that thing out on a level area onto the gravel part, turn a 90-degree corner and roll it out of the grass. And I mean, I don't know anything about construction or costs, but that would be seem to me to be a less work solution.
What's
I'm willing to pay up front if I don't have to keep paying every time.
Oh yeah, picking up, assembling it and putting it back in the observatory and all that, yeah. True.
Yeah.
Here is that it slopes two directions. It slopes this way and it's
Yeah.
Yeah.
So
Mhm.
it's on an angle that the line up here is not parallel.
This line is not parallel. No. It's not.
Well, but you're right. Would we be able to fill it in? You might be able to fill in that area and then come in this way. Right? So instead of going out into where the car is parked, you come out and then go towards where the person is standing to take the picture. That's another way to approach it.
The other way.
The
I
other,
mean, angle it this way.
but then the gravel and that's not,
Well, but
and you don't want to go
a
that,
bunch of concrete in anyways.
but well, I don't know if that's concrete or just dirt or what, or more gravel. But this way is where you want to take the scope because you're observing over here.
Yeah.
Yeah, you're gonna go over here.
Having a car run over
Yeah. I'd only put the concrete out so far because cars do come through here. We do have that. Plus, you have to remember, there's another group that comes out with that lawnmower that, I forgot the type, but it's the riding lawnmower so big and everything, it cut all the grass out of there. See, I'd probably gonna put the concrete so far out. Like to the edge of this building out here maybe, might come out about 6 feet down. If you wanted to make it all concrete, you could dig it out and do that.
Gravel dirt.
Well, there's gravel here already. I wouldn't go back to gravel and dirt. This, a long time ago, I used a concrete that was like the type you had for you're building your decks and that, where you pour the dry stuff in and then it hardens over time. If we do pour concrete out here, then everybody that comes out's got to bring 5 or 10 gallons of water so we can mix this and get this straight. Because if you're I've mixed concrete for some small sidewalk sections, but you still have to mix it and set it up right, dry it, and make sure it's you don't want it runny and thin and all that kind of stuff neither.
Another,
Okay, go ahead then, Jim. Go ahead.
are we even gonna be allowed to do this? It ain't our property.
It ain't our property, but as for maintenance and operational activities as guidelines, they might, or they wouldn't have ever let this happen, but I can always ask and find out.
You're making it ADA compliant.
I don't know if you can go that.
Well, it'd have to be poured a certain way. It'd have to be a certain width to be that.
I think, we figure out what we want and then we do it. And the university basically isn't gonna care unless we ask.
Yeah.
That's pretty much been the way things have gone on
Yeah.
out there for the past 20 years.
Well, since 2013.
My feeling is, making a decent slope to the edge of the gravel and then at the right angle to move on the other slope would be probably what we end up doing and just take enough water and cement out there to make it happen. But, that we can't figure out from the pictures we've got to go out there and actually, take real measurements and calculate it all out.
Oh, yeah, yeah.
But I'm almost positive that, the cement that we would need, quickcrete or whatever, would be a whole lot cheaper than buying one of those rings.
Right.
Oh, no.
Oh, well, no, that's true too. If you did a cement where it would be, yeah. There's no argument there, because I mean,
Be more logical.
yeah, and then you just leave it that way and you wouldn't worry about picking it up and carry it back in and stuff like that too. So yeah, that's fine. It's all right.
As far as ADA compliance, when you think about it,
No, but it wanted to still cement slab.
but ADA compliance, the thing is, they've got to get to that point anyway, and the trail is ADA nightmare, which
Right.
anybody to take advantage of an ADA compliant ramp would have to be driven down there, and once we're conducting the open house, that's not cool.
And so they get, so it's ADA compliant for them to get into the observatory. Then what?
Well, we're not
We're not ADA compliant to get into the observatory.
gonna be able to.
Yeah.
Something that's gonna be ADA compliant.
Yeah,
That's,
Like a
that's,
portable-
we're talking about, 5 figures to
Yeah.
make that really work well.
Yeah.
And, a lot of construction and plans and going through the university, because we're talking about a permanent structure. You put down concrete there, and somebody comes up with a jackhammer and they can make it go away. But, what we can actually afford to do is the ramp thing that Jack has looked into, or possibly a concrete mitigation to make that slope easier to navigate with that telescope, which is the main reason we're talking about this at all, because ADA compliant is just beyond us.
yeah.
And would this building be, is, what out there on the hill is?
Yeah.
Is the radio observatory ADA compliant? Isn't it the old, these are all quote. Shut down, I don't wanna use the A word. So it's, this all may be, talking about ADA may all be a moot point anyway.
Okay,
I don't expect anyone in a wheelchair to ever actually show up.
Right.
well, I remember years ago, we
Yeah,
did
we
have
did
some
have
people.
somebody.
And I pulled out the wooden plaque for the, that visitor sign, put all those together. And we got them rolled up there. Yeah, I admit it's been a few years, but.
This couple of like 3x6 pieces of half-inch plywood would be all you really need. They'd be light enough to move in and out. Big lots.
Even plywood has got pretty heavy feet.
Yeah,
That can be.
It's like a half inch, not 3/4, and
Yeah, I built a ramp for my dog.
Has anybody got a really big 3D printer?
Woo. Okay, we'll leave that, I'll leave this up for discussion later, but I want to bring it, because I know we talked about it. We talked about it last year, at the end of the year, it's kind of like, so I'm bringing it up again to continue. And do you want to talk about this?
I don't know, was you gonna bring up the swap meet or no?
That was on my list, but I don't care what else, but
Okay, he's got the flyer right there.
Okay, here's,
flyers.
Yeah.
for those of you that are interested, again, is the annual swap meet for Amateur Astronomy Club. And, admission is 7 per person, tables 25 in advance. We did this a couple years ago, or last year, because we had some parts from one of the old telescopes. There's a 4.25 inch secondary mirror in that. And I wanted to see if we could sell it there, and we rented a table. What we're asking is, would there be any club members interested in selling any of their stuff? We're thinking just renting a club table, bring your stuff out there and sell it. But you still have to pay the $7 entrance fee. but you wouldn't end up spending $30 for a table, so. I mean, you probably don't need the whole table, it just needs, or put your stuff on, so. Something to think about. What we could do, and I'm gonna try and sell the 4¼ inch mirror, the other stuff from the club, so I'll get one table to start with. And to take it from there, I guess.
I believe,
Oh, yes, and then you do check up here. They do have some lectures there, different types, and there's gonna be a lecture on smart telescopes, so.
So Jack, are you going to have a table, or is someone going to have a table?
I'm gonna go again and buy a table, yeah.
Are you willing to share that?
Yeah, I did that last year. Matter of fact, there's 2 or 3 people last year. There was Mike Hagan and another guy. Yeah, that we had all kinds of stuff out there set up. And we sold some other club stuff too, like a couple of the old tripods and some other mounts and other things in that too. So that's how we got some of the stuff out of the club. We've got a little bit more room in the storage area. But other than that, yeah, do that again. And then it's going to be for March 28th. And then we have a club meeting, I think, on March 20th. But I'm going to go ahead and order one table anyway and take it from there.
How big is the table?
I think they're about
You like this one?
Yeah.
something like that one, maybe a little bigger. Yeah.
Tables, they have a big telescope, big shed sit down.
Oh, they just set the telescope out in front. Yeah. That's what most people did. Matter of fact, I had one small scope on a tripod. I set it out in front. And the other people, I think Mike Hagan had a bunch of his stuff. Somebody else had some stuff they wanted. They just put it all on the table. We just sat there. They'll give you 2 chairs. So, with the table. So if we have a whole bunch of people, you might want to bring an extra chair. Okay?
Jack? Jeff?
Jack's got them.
Oh, yeah.
Okay, on Monday, Tim Miller and Barry Chapman, our webmaster and another VP, we had a meeting to basically figure out where we're at as far as the website movement. Tim has been working diligently and has everything that is basically publicly facing, so like our outreach stuff, membership information. I know the young astronomers pages are intact in some fashion. The things that aren't there are like the members only pieces and whatnot. That's what we're gonna basically save for the step 2. Everything looks good. I do know that on Sunday, the waiting period for the domain transfer is going to expire. So at that time, our domain transfer will be transferred to Barry's provider, and we'll have full control over the domain from HostGator. Our contract with HostGator ends on March 15th, which means they're probably going to renew as soon as they can. But we've got probably a couple of weeks here that we're going to collect all the stuff that's been submitted to the current WordPress site, back it up, file transfer, write whatever scripts we need to move it into the new one. Barry says that should be a piece of cake as far as the files, because I guess they put them all in one big spot. So all of our photos, PDFs for the newsletter, all that kind of stuff can move over. That's one of the things Tim's been working on, is to make sure that that newsletter interface is working. And during that meeting, they actually went into a coding section and did some things to make sure that this is going to be basically easy for Amy or whoever the newsletter editor is. They'll produce a PDF, upload a file, fill out the appropriate database stuff, submit it, and boom, it's going to magically go online. And that's the pieces they were scraping out. On Monday night during the meeting, it was like a 2-hour meeting. It was like, we have to do this now. But things are rolling along. I'm confident that, we're on a good track. We shouldn't have any problem with retiring the HostGator site and moving on to the Berry site, which I think, if I can find where the heck my browser is, I'm gonna see if I have that up. Of course I don't. I just gotta hope to show it. Of course I don't have a link here. Not a biggie. I'll send it out soon. Barry's been working on it. It's like something. I forget the URL constantly, and I have to ask him every time. Make sure I took notes from what the public stuff, the domain, yes. The fact stuff I printed out 3 of the brochures for the Ford swap meet thing there. If anybody wants to take one for a reminder. And I have, let's see, 5 handbooks and 6 calendars for the RASC materials still available. Pay Doug directly or me. If you want to pick one up tonight, I can deal with cash. We'll deal with payment somehow. But if you want them, we still have some available. And the last thing, well, almost last thing. Let's do this first. I don't know how many of you guys got messages, but I got a letter from the Astronomical League because, I got a membership. If you have a membership, you might have gotten one of these things. But it's basically, they've had some problems with some false Venmo payments. So if you ever get, approached by somebody who's representing themselves as the Astronomical League, they're phony. The letter at the bottom says, the bottom line is no officer of AL will ever send you a request for assistance in making payment, purchasing a gift card, or engaging in any financial transaction. So if you see anything like that, it's phony, delete it and move on. Yeah, and they said that they've had some problems with this in the past, and it's kind of got a new stronger wave of this going on. So they sent out a notice. I know many of our members are members of the league, so I figured I'd set up. And I did finally finish this book, which I forget the publisher here. They sent us a free copy. Bright Publisher, I believe it, and they just to evaluate whatever. And it's called The Living Universe. I checked it out. It's fairly well written. The beginning chapters are a little wavering, but it basically is kind of a layman's view of everything about the universe, down from physics and planet formation to galaxies and the whole kit and caboodle. So
they put it all in there.
They put it all in this very thin little book. There's no pictures or diagrams or anything like that, which I did give them some feedback that that would be very handy. But it was a pretty decent book. Yeah, I mean, a lot of it was review. I probably review for, many in here, but if you have a beginner or somebody who's looking for it, it's not a bad book. And I know you can get it online, but they sent us a copy as a club free. So wanted to take a look. Let me know if you check it out. We can track it around or, pass it over to other members. And I think that's all I have on my list, though. Charlie. Any questions, of course, we'll figure out the video on this thing some century.
So that is all of our officers. I don't think I see any in the Zoom audience. Jim.
Mayberry State Park is having a public astronomy day on March 21st. I believe the officers got notified about this. And this is kind of stuff we do. It's also the night for the Messier Marathon. So you'd have to make a choice about what you wanted to do. There are things to find out about how things are going to be set up for their astronomy night, because we were out there a couple of years ago for astronomy at the beach, and because the park Island Park had been closed down, for construction. But, that site worked out pretty well for, this kind of family oriented, observing section. So. Don knows something about it. Yeah, so I looked up the website for the Friends of Mayberry State Park. And I asked them if they needed any additional telescopes or help. I have no idea who they're looking at. My guess is maybe the forestry. But I have gotten no reply. Okay. I guess when we find something out, we'll let everyone know.
Does anybody have anything else? Do I hear a motion to adjourn?
So moved.
Support? Anybody opposed? You haven't opposed that for a long time, Doug.
What?
He's thirsty.
You always oppose something. Okay.
Oh, kick something. That's from the worst. Good show.